Atom styles in LAMMPS. This tutorial is about the format files of some atom styles. This is mainly used when carrying out coarse grain molecular dynamic simulations. So, for coarse grain molecular dynamic simulations, there are different types of coarse grain atoms: point, spherical, ellipsoidal, linear, triangular. We also can create hybrid sets of atoms. There are some file formats specifically designed for this kind of atoms. Here we present file formats and scripts of some of the most important kind of atoms. Coarse grain models. So basically, the coarse grain models replace real atoms by effective atoms using coarse grain models. So basically, these reduce degrees of freedom in the atomistic models by integrating out. This is done by discarding irrelevant variables based on multiscale concepts, preserving relevant properties. There is a mapping process from the atomistic model to the coarse grain model called coarse graining. In this process, there are also coarse grain potentials. For example, a polymer chain can be modeled using different coarse grain models. The rod bead model, the bead spring model, and the bottleneck lace model. This is not precisely a real polymer, but represents some property of the polymer called elasticity. However, this model shows to produce different thermodynamic and statistical properties of a real polymer chain. In this process, there is overlapping of length and temporal scales. For example, the diffusion of colloidal particles and polymers in water, where we disregard bond and quantum orbitals information. In addition, there are also another kind of molecules or macromolecules, such as membranes, which can be modeled by using some simplified models, all basically using particles, point particles, and springs. Coarse grain model advantages. So, we save computer resources, we save time and memory. We also reach longer time scales. We can use larger systems, and we simplify the molecular modeling. In addition, comparison with scale theories can be carried out. Atoms in LAMMPS. There are point, spherical, ellipsoidal, linear, triangular, coarse grain particles. For example, the bead spring models we have mentioned before. Colloids, membranes, liquid crystals, nanoparticles, and charged particles are some of the models used in LAMMPS. Okay, so atoms in LAMMPS. So in order to carry out a molecular dynamic simulations, it is required an initial configuration. This initial configuration can be created by using LAMMPS instructions, but also can be read by using a file data. This file data has certain structure. Let's see. So, the atom in LAMMPS can be written in certain data files with extension .data. For example, name.data or data.name. Both are valid LAMMPS files. These files provide details about the number and type of the atoms, bonds, angles, dihedrals, ellipsoids, and impropers. It is also provided information about the box simulation, information about the potential, the coordinates, velocities, molecular structure, where bond, angles, dihedrals, impropers, ellipsoids information is provided. This is required to know the structure or the architecture of the molecule. LAMMPS employs a destruction rate data to load the data files. Here's an example of a simple script where the read data instruction is employed. In this, we have a simple Lennard-Jones melt using the atomic atom style. Here, the initial configuration with the atoms is loaded using read data and then the name of the file. We also can write the final configuration using the instruction write data. Here we use a different name for the output file. Atom in LAMMPS, the file data structure. So data file with extension name.data provides the information we have explained before. But there are different details, different formats we can use to build a data file. In this table, we see different kinds of atoms: angle, atomic, body, bond, charge, dipole, DPD, EDPD, MDPD, TDPD, electron, ellipsoid, full, line, meso, molecular, peri, SMD, sphere, spin, template, tree, wave packet, hybrid. Every kind of atom has certain structure. For writing the file .data. For example, atomic. Atomic has the atom ID, which is an integer number, then the atom type, which is an integer number also, and then the coordinates of the atom. Similarly, the bond, atom style, uses atom ID, molecule ID, atom type, and the coordinates. Ellipsoid, the atom ID, the atom type, the ellipsoid flag, the density, and the coordinates. Every kind of atom has certain characteristics that must be included in the data file. The specific structure of every kind of atom style will be described as follows. Okay, case number 1. Point particles. The first atom style we discuss is atomic. The atom style atomic is used for point particles with mass and translation velocity. We also have non-bond interactions among the particles, such as Lennard-Jones, Gaussian, soft potential, weak channel Anderson, etc. Examples of this atom style are simple particles such as argon, neon, iron, salt, and colloidal particles without structure. Okay, the file format of using the atom style atomic. Atomic employs a header where atoms and types of atoms are described. We also show the simulation box dimensions. Then we must include masses, the mass of the particles, the Paris coefficients, indicating the potential we are using. In this case, we use the Lennard-Jones cut potential. Coordinates. Here we specify the structure or the position of the atoms. The first column, we need an atom ID, which is an integer number. Then it comes the atom type, another integer number, and then the coordinates of the particle. Sometimes we can include these parameters that are the number of crossing on the simulation phases box. Then it comes velocities, where we have to provide the atom ID and the velocities coordinates. Right, here we see a file format for atomic style, atomic. For that, we use the Lennard-Jones melt atom style atomic. We use units, Lennard-Jones units, atom style atomic, and per style Lennard-Jones cut. Then it comes the section where we load the file called atomic.data by using read data, and then the name of the file. It comes the information for the simulation, like per coefficient, neighbor list information, the fix for the thermostat deploying the simulation, and some additional information. In addition, we can include write data to store the final simulation of the system. Case number 2, spherical particles. Here we use the atom style sphere. In the atom style sphere, we use spherical particles So the spherical particles has diameter, density, and angular velocity. For this type of particle, we use non-bond interactions using extended Lennard-Jones, colloid, extended Weeks-Chandler-Anderson, and Gauss potentials. The atom-style sphere is employed for spherical particles, such as colloids, and nanoparticles with linear and angular velocities. We can change the diameter of the spheres and the attributes of the particles. The file format for atom-style sphere. We have a header where the number and types of atoms is described, and then information related to the simulation box dimensions. We can include information such as the mass, the Planck coefficients, and then it comes the coordinates. So for this specific format, we use the following: atom ID in the first column, atom type in the second column, then it comes the diameter, the density, and the Cartesian coordinates of the particles. After that, we have to describe or to include the velocities. So, the first column we have the atom ID, the velocity components, and the angular velocity components as well. Recall that the sphere particles have structure, so we have angular velocity because the molecule rotates when receiving torques. Okay. File format for atom-style sphere. Here we have a LAMMPS script showing a colloid Lennard-Jones particles using the atom-style sphere. We also use Lennard-Jones units using the atom-style sphere. Information about the neighbor list is employed. The peristyle, that is color in this case. Then it comes read data, where we load the file sphere.data. And information related to the potential coefficients. We stress that the read data instruction should be included just after the peristyle has been defined. Case number 3. In here, we use ellipsoidal particles. We use the atom-style ellipsoid. The atom-style ellipsoid uses different properties, such as the density, the shape, the quaternion, and the angular velocity. These parameters are required because these particles are anisotropic and possess certain orientation. For this atom style, we only have non-bonded interactions. The non-bonded interactions are introduced by using the Guy-Byrne potential, that is an anisotropic version of the Lennard-Jones potential. The atom-style ellipsoid is used for mesogenic ellipsoids. These are liquid crystal formers, anisotropic molecules, such as DNA. So the file format for the atom-style ellipsoid is as follows. First, we need a header where we specify the atom's number as the ellipsoids, and finally the types of atoms. This ellipsoid refers to the ellipsoid shape of the particles. Then we must define the simulation bulk dimensions. Next, the pair coefficient needs to be specified, indicating the potential we are using. Coordinates. So, the format for the particle coordinates is as follows. First, we include the atom ID, which is, again, an integer number, the atom type, indicating by an integer number, ellipsoid flag, which indicates this is an ellipsoid particle, and then it comes the density. So after specifying the density, the Cartesian coordinates are written. Velocities. In this section, we must specify the atom ID of the particle and then the Cartesian components of the velocity, followed by the angular coordinates of the velocity. Ellipsoids. In this section, we have to include information related to the particle structure. So, the format is as follows. In the first column, we have the atom ID, which is an integer number, followed by three numbers called shape X, shape Y, shape Z, indicating the main axis of the ellipsoid particle, followed by four numbers quad W, quad I, quad J, quad K, the quaternion vector. This vector indicates the orientation of the particle. File format, atom-style ellipsoid. In here, we described 10 ellipsoidal particles using the atom-style ellipsoid. We use the Lennard-Jones units and the atom-style ellipsoid. We first need to indicate the potential, that in this case is the Guy-Byrne potential. After that, we load the file ellipsoid data using read data. Follow by information related to the perk coefficient, the neighbor list, and the thermodynamic ensemble. In this case, we use the MVT ensemble using the special instruction as sphere because we have to include the angular motion of the ellipsoidal particles. So this is indicated by using this instruction. And then the thermo, time step, and run, indicating the number of iterations. Case 4. Bit spring model using atom-style bond. This atom style is used for modeling polymers, such as this star polymer or linear polymers. So, in the atom-style bond, we can model coarse grain polymers by using the bit spring model, where point particles are linked with springs using the Kramer-Grace model. So the Kramer-Grace model only includes point particles and elastic springs. So in this case, we have bonded interactions and non-bonded interactions. In the bonded interactions, we have the Finney and the harmonic potentials, which takes into account the elasticity of the molecule. Next, we must include the non-bonded interactions between point particles. This is done by using the Lennard-Jones potential, the WCA potential, or any other potential such as the soft potential and the Gauss potential. By using this coarse grain model, we can simulate the motion of linear, ring, branched polymers and other structured molecules such as polymer brushes, elastic networks, gels, etc. Okay, the file format for atom-style bond. First, we need to include a header with the number, atom, and the atom types, and the bond and the bond type, followed by the simulation bond dimensions. After that, we specify the masses of the particles, the bond coefficients, and the perk coefficients. Right, so the file format for atom-style bond continues for when including the coordinates, and then we have the following structure: the first column, the atom ID, the molecule ID, the atom type, and the coordinates of the bits or the point particles. Here we have something new, that is the molecular ID, because we can have different molecules. So every atom is associated with certain molecule. And then we have to specify the velocities. So for the velocities, we also have in the first column the atom ID, followed by three numbers that are the Cartesian components of the velocity. And finally, the bond section. So in the bond section, we include the structure of the molecule. Could be a polymer, it could be another structure, but we need to specify how the molecules are linked. So in the first column, we need to have an ID, bond ID, then a bond type, and then the two particles that are linked by a specific spring, just like this. So by using this format, we specified what atoms are linked and what kind of bond we are using. Okay, so the file format, atom style bond. So we have script where we simulate a star polymer using the bit spring model. Again, we use Lennard-Jones units using the atom style bond. For the springs, we use special bonds, in this case the Finney spring, and we must include the bond style. As I said, we use Finney. The price tag for the non-bond interaction, the Lennard-Jones cut potential, followed by certain instructions indicating the kind of potential. This is the WC potential instead, and the sentence read data. So in this case, we are loading the bond data file where the structure of the polymer is included. Next, the information related to the per coefficient, in this case the Finney potential, and the per coefficient for the Lennard-Jones potential. And then we can include more information, but here is just the thermal times Stipend run as in previous examples. So this being an example indicates how to load the bond data file. So this is the minimal information we require to run this script. So as you can see, it's a very short script. Okay. Case number 5. So in case number 5, we have a semi-flexible bit spring polymer. So in this case, we use the atom style angle. So for this, besides the bits and the springs, we need to include certain restrictions in the bonds. So that makes the polymers rigid. There is certain stiffness. So this stiffness is included by using an additional potential that gives us the semi-flexible features of the polymer. So we have rigid molecules by using this additional potential. As I said, we have a bit spring model with bonded and angle interactions. So this is very similar to the bond atom style, but with the difference of this new contribution, the angle interactions. So in the bond interaction, we have to include the elastic potential. Could be the Finney potential or the harmonic potential. But now we are to include the harmonic or cosine or sine angle potential. This potential hinders the angles between the springs. Right, and then the non-bond interaction comes. We can use the Lennard-Jones potential, the WCA potential, weak channel anesthetic potential or some sort of soft potential. And then, as I said, you can have linear, ring, or branch semi-flexible polymers. Here we have a linear semi-flexible polymer where we can see the rigidity of the molecule, so the physical properties are different from the atom style bond, and we can construct a dilute solution of stiff polymers, for example. And well, we have the file format for the atom style angle, as well as in the bond atom style. We include a header with atom number, atom type, bonds, bond types, angle, and angle types, followed by the simulation bug dimensions. Then we specify the masses, the pair coefficients for the non-bonding interactions, the bond coefficients for the bonding interactions, and then the angle coefficient. This is the new contribution. Then we have to specify the coefficients for the angle interactions. Right, so the file format for atom style angle is very similar to the bond atom style. So in here the coordinates are specified in the same fashion that indicates for the bond atom style. So atom ID, molecule ID, atom type, the coordinates, the Cartesian coordinates, and then the velocities, so the atom ID, the Cartesian components, the velocity Cartesian components, I mean, and then the bond. So the bonds are specified as we explained previously by using an ID, bond ID, then the bond type, and the ID of the linked particles, particle 1 and particle 2. Next, the angles. So for the angles, we need to specify 3 particles because the angle between the springs is formed by using three particles. So we need to specify the idea of the angle type, and then the particle that forms the angle. So particle ID, the ID for particle 1, the ID for particle 2, and the ID for particle 3. So within these three numbers, we are including the angle, the particles that are used for calculating the angle interaction. Okay, so this is a minimum script where we show a simple semi-flexible polymer, single semi-flexible polymer, using the atom style angle. So the file format, atom style, we use angle. As you know, in the previous script examples, we use the Lennard-Jones units, followed by information referred to the bonds. We use the finite bond, some information related to the neighbor list, and then it comes the bond style, that is finite, and the angle style. This is the new contribution, where we use the harmonic angle potential, and then we use the Lennard-Jones cut potential, that is the WCA potential. And then it comes the section where the angle.data is loaded using read data, followed by the instruction referring the potential coefficients for the WCA potential. Then it comes the bond coefficient for the finite potential and the angle coefficient, where here we have information related to the spring stiffness constant and the maximum angle. And then information of the ensemble we use. In this case, we use the Langevin ensemble for equilibrating this semi-flexible polymer. Okay. Case number 6. Spherical particles and polymers. For this, we use the Atomistic Hybrid. So when we use the word hybrid, we are mixing two kinds of atom styles. In this case, we are using the angle style we have explained before and the sphere style we have explained before. So this is a combination of the properties of both atom styles, angle and sphere. There are another combinations. It could be a bond sphere, it could be I don't know, it could be bond and ellipsoid. So there are certain allowed combinations, but in this example we are working with this example. So here's some nanoparticles where we use the spheres with connected polymers. So we use both the sphere and the angle for describing this system. Right, the Atomistic Hybrid. So as I said, hybrid atoms are made of spherical atoms linked with bonds and angles. So we can link to the spherical particles some polymers, like these two coarse graining molecules. So the spherical particles are here, and then we graft some semi-flexible polymers. In this case, we have flexible polymers and some spherical colloidal particles. So both examples can be constructed by using this hybrid angle sphere atom style. Both examples need the extended finite potential, that is includes the size of the particle, and we have the harmonic potential as well. So the same is true for the extended angular harmonic, where we need to include the size of the particle. For the non-bonded interactions, we use an extended version for the Lennard-Jones or WCA potential called extended Lennard-Jones. This potential is employed for considering the different diameters of the particles. So we can have two different kinds of particles, and then we have different diameters. This atom style is very useful for constructing blends of polymers, colloids, molecular polymer brushes, or uncoated colloidal particles. Right, so the file format Atomistic Hybrid angle sphere has similar structure that the previous scripts we have presented. So we have a header with the number, the type of atoms, bonds, and the type of bonds, the angles and the type of angles. So this is very similar to the angle, the atom style angle, I mean. So we also have to specify the box simulation dimensions, followed by the mass or the masses of the particles, followed by the non-bounded pair coefficients, the bond coefficients, and the angle coefficients. Here we need to be very careful when constructing this coefficient, because it's not that straightforward as the Lennard-Jones system. Here we need to consider the different diameters of the particles and the different spring constants for components of the molecules. So different spring constants are used, different equilibrium lengths, and the size of the particles. The same applies for the angle coefficients, where the spring constant need to be introduced and the angle, the maximum angle of the interactions. Okay, so the file format of the atom-style hybrid for the angle sphere example. Then we have to include the coordinates. So this is the complicated part, if we can call it like that. In this case, we need to use the atom ID. We use atom ID as in previous examples, followed by the atom type. And then we use, we put the Cartesian coordinates of the particles, followed by the molecule ID. The molecule ID is an integer number, and then the diameter of the particle, and the mass or the density. Here we can use the density for the spherical particles. So in this case, this particle is spherical, and then we use the density. But for the angle or the bond particles, this is just the mass. In this case, we have 0 here because the angle and the bond particles have no diameters. So these are just point particles. So this is why here we use 0. And 15 is because this is the diameter of the spherical particle, but 0 for the fini or the angle particles. Okay, next we need to include the velocities. So we need the atom ID and the Cartesian components of the velocity. We can include the angular components of velocity. In this case, the only component different of 0 is the component of this particle, the spherical particle, followed by the bonds, atom ID, bond type, ID particle 1, ID particle 2. So it's pretty similar to the angle atom style. Atom ID, angle type, ID particle 1, ID particle 2, ID particle 3. So this section is basically the same that for the case of atom style angle. The only difference in this hybrid script is how we set the coordinates. So here we first set the Cartesian coordinates of the particles, followed by this information, the molecular ID, the diameter, the mass or the density. So this is the only thing that changed. Okay, so we have the file format for the atom-style hybrid angle sphere. So this is an example for some spherical particle of diameter d with some polymers attached on the surface of this particle. So this is a good case for studying using the atom-style hybrid angle sphere, because we have only one spherical particle, and we have polymers attached to the spherical particles by means of an angle interaction and point interaction. So we use the Lennard-Jones units, and we have to specify additional information because we have different particles involved in this example. This section is referred to the neighbor list. Then we define certain variables necessary for the potentials. So we have one central particle, and here we have the diameter of the particle. So the bigger particle, the spherical particle, has a diameter of 15 in Lennard-Jones units, and the diameter of the monomers or the bits is 0. Well, here we use 1, but it should be 0. And then we need to specify the energy interactions, the cutoff of the potentials, and this variable delta is for the extended potential, the extended version for the Lennard-Jones potentials and the finite potentials. So this is necessary because the particles have different diameters. And we use these variables for defining the peristyle. Here, as I said, we use the Lennard-Jones expand potential. This cutoff is for the central big particle. And then we also have to define the boundary style for this. So in this case, we use the finite expand potential. For the angle interaction, the angle potential, we use the harmonic. So basically, this is the interaction between the central core and the polymers. So it's the Hooke's law, and well, it comes the section where we load the data file. We call this hybrid data, and by using read data, we access to the structure of this molecule. For convenience, we define two groups using group, monomer and core. So monomer is for the polymer, and core is for the central particle. Next, we have the pair coefficient. So here, this is just information related to the extended Lennard-Jones potential, where we have to take into account the different size between the central core and the monomers. So this is included by using this variable delta. So this is interaction between the monomers and the core, whereas this and this correspond to the monomers, interaction between monomers that forms the polymer, and this corresponds to the interactions between the central core. We see there are different parameters for the cutoff potential. So these are defined here. The cutoff for the central core potential is this number. This is obtained by taking into account the particle diameter times 2 to the 1/6, and here is simply the WCA cutoff distance. Next, the bonding interactions are included. So we have the finite potential for the monomers. So this is basically the same that employed in the bond example, with the difference of this zero. This zero is just for indicating that these particles have no diameter or have no structure. And this is for the interactions between the big particle and the monomers near to the surface. So we need to include the parameter delta. This delta is the diameter of the big particle minus the diameter of the small particle among two. Finally, the angle coefficient needs to be defined. So the spring constant in the Hooke's law is 200, and this is the maximum angle, 104.51. So this is the degree, the maximum angle. And then we split the motion of the two particles. Here we have the motion for the core, and this is the motion for the monomer. We employ the Langevin equation by using MVE and Langevin together. So the only thing that is different is the friction coefficient. The temperature is just 1. This is just the seat of the Raman generator, and the thermal information, the time step size, and run. So we run this for 10,000 times. Right. So the complicated issue about these systems is the construction of the data files. For some very simple examples like sphere or atomic, the construction of these files is very straightforward because this can be treated as point particles. So the only thing is setting a spherical particle. This can be done by using some LAMMPS instructions. So as long as we don't have bonds or angles, this is very straightforward. So writing a script is not worth the effort. What is more tricky and time-consuming is writing the configurations for the polymers or networks or some sort of bonded molecules. So this can be done by hand, by writing some code. So a very simple code using Python or C can be implemented for these very simple examples. So this is the and then replicate the molecular coordinates across the simulation box. This can be done by using some LAMMPS tools like molten plate or other tools available on the internet. Okay. Well, for this tutorial, you can find the data files and the scripts available on my GitHub that is specified here. And you can see some examples of how using this can be convenient for constructing polymer structures. I can show you some of my examples in my YouTube here's the links, so you can check that. And well, I thank you for your attention, and I hope this can be helpful. Thank you very much, and see you next time.